innovative aspects that we decided to summarize in the title of fractal structures relevant for thermal energy storage. So my name is Adriano Sciacovelli, and I'm associate professor at the University of Birmingham and the Birmingham Center for Energy Storage. So I lead the work package in the ThumbsUp project that looks at the latent heat thermal energy storage component and innovations. So it's an effort among many partners. And I want to mention, obviously, as University of Birmingham, TES, University of Yale, plus Cardiff, and many others. So what I would like just to perhaps, let's say, outline as objective of my presentation for the discussion, the conversation, is a bit of how we approach the development and the innovation of the component itself. So the actual functional unit that delivers thermal energy storage with the, let's say, underpinning principle of latent heat energy storage. So I'll just briefly touch upon kind of basic principle just to establish a bit of a baseline, and then let's say give you an overview about how we approach the innovations and the development of some key components, some heat transfer equipments that are part of this device. And that's pretty much the outline of this presentation. So for those of you, and I'm aware that there were a couple of hands raised before, in the ThumbsUp project, by and large, from technological point of view, we look at pretty much across the entire time scales of thermal energy storage, from short duration to long duration. On the short duration side, let's say the core technology is a PCM-based or latent heat storage system with, let's say, intended overarching scenario applications that are summarized in this graphical abstract that we use regularly for illustrating the project. So we look at compact phase change material thermal energy storage systems at both centralized location at building scale and decentralized. So centralized means typically near the heat or cooling generation assets of the buildings. These could be actually substations of district heating network, could be heat pumps, it could be other, let's say, local renewables. And decentralized means near the delivery point. So let's say at apartment level or near the heat delivering devices like radiators or underfloor heating systems, with basically three main overarching applications. One, obviously, maximizing the use of renewables, local renewables with the power to heat approach. So typically heat pumps, chillers, etc., integrated with storage for charging and discharging at convenient times. And convenient is open for debate if you want. But more, let's say, I would say uniquely also to rectify inefficiencies. The decentralized solutions particularly aimed at rectifying inefficiencies in delivering of heating and cooling. Typically, there are some issues in existing buildings on oversizing, temperature control, mismatching of temperature supply and returns, and thermal energy storage might help to resolve those, and hence this idea of a short duration, centralized and decentralized in buildings. So from a, let's say, technological point of view, as I mentioned, it's a multiple effort. As core technology providers, we have, let's say, TES company that will speak after, but we look as at archetypes, so to say, of integration with the supply and the generation. Obviously, a thermal energy storage that can integrate with the heat pumps and potentially other power to heat converters, local renewables, both solar and thermal. And on, let's say, on the supply side, or if you prefer, on the discharger side of the TS, provision of space heating, space cooling, and domestic hot water as typical applications in discharge phase of the thermal energy storage system. So for those of you that are familiar, this slide will look probably quite familiar indeed. So we are exploiting basic principle of first order transitions or phase change, if you prefer, to store thermal energy. So it means that we take advantage as, let's say, in any PCM-based thermal storage unit of a process of melting and solidification of dedicated materials, and there will be some these webinars also dedicated to the material aspects. But in general, broadly speaking, in our domain of interest, in the project of interest, and the domain of interest of the project, we are looking at, let's say, temperature ranges that for the hot storage, so for space heating and domestic hot water, between 40 to 60 degrees C as a broad melting, let's say, range. We might have multiple options in those in that range, while in the cooling side, something that is typically between, let's say, 7, 9, and 13 degrees C for cooling applications. So obviously there are multiple key components and key parts in a thermal energy storage unit. And this is something that will be reiterated also by ITES after this presentation. And it's a multi-scale problem. It's a multi-scale problem that obviously involves materials, material technology, material science, involves components and devices that interact with those materials and allow to deliver essentially the function of the unit, proper charging and discharging, and some also important elements of control and general, let's say, smartness of the system, where control and optimal operation strategy comes into play. One of the key focal area and focus of the next part of the talk is on the actual, let's say, intermediate scale involved in this system, in this latent heat thermal energy storage system. So in the heat exchangers and in the heat transfer components that interacts with the PCM and allows to either charge and discharge the system through, let's say, heat transfer processes. So you might be aware that there are, let's say, multiple possible approaches to look at what constitute a best optimal heat exchanger for latent heat thermal storage, or for a latent heat thermal energy storage unit. And let's say the literature and in general the attempts that have been tried over the years have heavily relied on, let's say, taking advantage of traditional, let's say, supply chains of heat exchangers. And you see some examples here from the typical, let's say, finned heat exchanger to macro encapsulation to plate type heat exchangers. Pretty much all the time with the intent and the purpose to overcome the basic challenge, which is the limited heat transfer performances. Phase change materials are attractive from energy storage capacity point of view. So in principle, they can lead to a system with a smaller footprint, but they are typically characterized by low thermal conductivity. So this means that the heat transfer interaction between the heat exchanger in contact with the PCM is relatively challenging, i.e. it's difficult to inject or extract rapidly and effectively thermal energy from the PCM. So we have substance that allows high energy storage capacity, but we have the challenge of charging and discharging this substance effectively. And over the years, as you can see also in this slide, there's been multiple attempts on how to approach this from a component perspective by using a number of techniques to enhance this phenomena of heat transfer between the PCM and the heat exchanger where the working fluids operates. What we specialize in, this is a kind of core area of interest and expertise at University of Birmingham in our team, is to look at this problem from a slightly different angle. Point one, we have, and there is, let's say, growing evidence that the traditional heat exchangers that are existing for many decades are not necessarily ideal for the purpose of application in latent heat thermal energy storage units. To put it in other ways, there is growing evidence that unconventional, more bespoke geometries and configurations are needed to overcome this heat transfer challenge, but also to cope with the fact that these systems tend to operate in intermittent conditions, i.e. they are either charging or discharging, and this is intrinsically a transient phenomenon. So what you see here is just some example of what that we've done in the past, and also what that is available, broadly speaking, in the literature, where we see growing attempts to come up with alternatives for these heat transfer, these fractals, sometimes called fractal geometries, to interact between the PCM and the working fluids. How we come up with these geometries, so what we do for kind of overcoming the traditional heat exchangers designs. So we developed, and that's part of what I wanted to emphasize in this talk, an approach that tries to overcome a bit the traditional way to look at the problem. So this is a bit at the interface from some fundamentals in thermal fluid engineering and applied applications like thermal energy storage. So typically, vast majority of attempts, both in academia and in industry, have approached the problem by what with this sort of cartoonish slide we represent on the left. People propose a certain geometry, a certain configuration, and then they try to modify parameters of this configuration. But typically this leads to relatively suboptimal design, because you are pretty much linked to what you have conceived at the beginning. While what we have done and what we try to do also in ThumbsUp for the specific needs of the project is to look at the problem from a more fundamental point of view and says, can we forget any initial assumption? Can we develop an approach that allows the geometry and the heat exchanger configuration to naturally emerge from the problem itself? So to say, a free of heuristic approach for those of you that are in optimization and non-parametric optimization problem, or shape optimization sometimes it's called. So I want to just give you let's say a highlight of how this work. And if you had to take perhaps one key message out of this approach, is that here we do not optimize any more parameters of the geometry, but we optimize distribution of materials. So these are very sort of archetype of a problem. It's a single tube, shell and tube thermal energy storage unit. And we ask ourselves this basic fundamental question. If we have a certain fraction of a domain that is occupied by heat exchanger material, let's say 20% of the available space, and we have complete freedom in distribute this material, how that look like if we want to maximize the performances? So we optimize the distribution of the material rather than parameters of the heat exchanger. There are a number of tricks here that are technical. Perhaps discuss them later if you have questions on how to represent this material and this let's say distribution of material and how to optimize it. But the let's say key second message that I would like to emphasize, that we essentially proceed with a problem that combines the physics of the latent thermal storage units, so it allows to describe the melting and solidifications, and allows this geometry to naturally emerge from the physics of the problem, rather than from an initial assumption of using a certain type of heat exchanger. So that looks like as follows. So in this chart, you will see, let's say, initial guess of the geometry, which is basically no guess. You will see on the vertical side, let's say, key performance indicator. Basically, the time needed for discharge this unit is the cross section of this shell and tube, and on the horizontal side, some optimization iterations. And what we have is, in this approach, emergence of the geometry that is essentially not assumed at the very beginning. The configuration that is optimal for the given problem is a natural outcome of the optimization problem. And what is interesting here from a kind of technical computational point of view is that we can tune the geometries to the physics of the problem. So what you see here is a split between a case of a, let's say, transversal cross-section of a case study of a latent thermal storage unit, where on the left, it's for solidification. So when we discharge the system. And on the right-hand side, instead, is the optimal geometry when we have the actual charging process for hot storage, for melting. So these, let's say, branched structures and fins tends to optimize locally the performance of the heat storage systems, and they are strictly related to the physical behavior of the system. So we don't need to guess from the very beginning what could be a good solution for the heat exchange. Last minute. Well, obviously, we gained quite a bit of performance in this case. In this case, it was a 30% improvement in the charge-discharge rates. And what is useful and what we are, let's say, expanding and doing in the ThumbsUp project is that once we have this approach, it's easily tunable for the same class of problems and different configurations. So what you see here, it's some, let's say, high-level summary of what we can also do with other type of configuration heat exchangers. In this case, would be more sort of plate type heat exchangers that interacts with the PCM and allows, for example, here to optimize the distribution of the fluid inside the heat exchanger for a different type of heat exchanger. And there are many challenges around this one. Many of those are related to computational aspects, other for realization and manufacturing, and a few of those are, let's say, embedded in the work program of ThumbsUp, and we'll demonstrate the geometries by also manufacture them in cooperation with the technology providers throughout the duration of the projects. And this will lead obviously to the final prototypes and high performance devices. So I'll stop here, Emilia, and